Okay, folks, so we're going to do a series of examples where we're going to be asked to graph these functions in their entirety. And we'll see that our tools of the first and second derivative will be enough to assist us in that, plus some additional skills that we've already done in this course. So when we get to class, we're going to actually lay out a series of steps for doing this, and we'll talk about those steps in class. But for right now, I'm just going to go ahead and jump into the problems, and I'll do the steps, and maybe you can guess what those steps are for completing these graphs. So the first thing you want to do with any function, in this case we're given the function f of x is this cubic here. The first thing you want to do with any function is you want to go ahead and state its domain. That tells you what values you will be allowed to plug into the function to begin with, etc. In this case, we have no restrictions on our domain, and it's a polynomial, and so the domain of this function is all real numbers. The next thing we want to always try to do is identify the zeros of the function. That's actually not a calculus skill at all, right? That's something that you learned how to do in an algebra class, to find the zeros of the function. So in this case, we're going to go ahead and set f of x equal to 0. And if we do that, we get 0 is equal to x cubed minus 3x squared minus 9x plus 27. And we're going to go ahead and try to factor this thing if we can. Okay, if we can't factor it, we'd have to use some other technique, such as Descartes' rule of signs, along with the rational roots theorem, or some other zero finding technique. But in this case, we can go ahead and factor this. If I go ahead and group these first two terms together, x cubed minus 3x squared, and then I'm going to add to that the next two terms grouped together. That's what we have. And notice that in both cases, I think I can factor out some of the components of the binomials, and in the first one we can factor out an x squared, and if I do that, that leaves me with an x minus 3 factor. And from the second one, I can factor out a minus 9, and if I do that, it leaves you with x minus 3. And the key to doing this technique of factor by grouping is after I've pulled out what I can from each of the two groups, notice I'm left with a common factor in each one, and so we can then take and extend this factoring by factoring the x minus 3 out of both those terms, leaving us with x squared minus 9 times x minus 3. So this factors to be continuing to factor. This gives us x plus 3 times x minus 3 times x minus 3, or if you like, x plus 3 times x minus 3 quantity squared. And so now we can go ahead and identify the zeros. What values for x will make this function equal to 0? That happens at x equals negative 3 for the first factor, or x equals 3, and it's probably worth noting that's of multiplicity 2. That is, that x equals 3 shows up as a root twice in this polynomial. So now that we've found the zeros of this function, the next thing I recommend finding in this order is to go ahead and find the y-intercept. So to find the y-intercept, if x equals 0 is in the domain, which it is in our case, but not in all functions, if x equals 0 is in the domain, find f of 0. So if we plug in a 0 into this polynomial, well, we'd have 0 cubed minus 3 times 0 squared minus 9 times 0. You probably already know what the answer is. And we get 27 out. So that means that the y-intercept, so the next step is the y-intercept. The y-intercept for this function is the ordered pair 0, 27. Okay. The next thing we want to do is comment as to whether there's any symmetry for this function. And, well, let's take a look at it. So here is our function, and the question is does this function display any symmetry that we can easily spot? And in this case, I can't see any symmetry to this. Folks, of the steps we do, the only step that's not required of you is this step about looking for symmetry. If you notice symmetry, if you know that this graph is, say, symmetric about the y-axis, or symmetric about the origin, or it's periodic, or something to that effect, if you notice that, you can go ahead and use that to assist you with the graphing, but it's not essential that you identify the symmetry for these functions. And for that reason, I'm not going to spend a lot of time discussing how you would check for symmetry. However, if you're interested, let me know, and I'd be happy to go through that. The next thing we're going to do is we're going to examine the exclusions in the domain. And why are we doing that? We're examining the exclusions in the domain to look for vertical asymptotes and holes. So So that's the next step, is to look for vertical asymptotes and holes. And I'm going to say in this case, this function has no vertical asymptotes or holes. Why is that? Well, there's a couple different answers to that. One, you could say it's a polynomial, and polynomials don't have vertical asymptotes or holes. But another way, and probably the more sophisticated way of answering that question, is to say, well, the domain was all real numbers. And if the domain's all real numbers, then you can't have any exclusions in the domain, and so there's no potential locations for us to have vertical asymptotes or holes. So the next thing we want to look for is the long-term behavior. So for the long-term behavior, this actually harkens all the way back to something that we did in Chapter 2. We're going to look at the limit as x approaches infinity of f of x, and we're going to look at the limit as x approaches negative infinity of f of x. Well, we've put f of x into factored form here, which makes it easy to answer this question. Oops, I don't think we have. Yeah, we did. We did up here. So we put it into factored form as x plus 3 times x minus 3 quantity squared. And so notice what happens as x gets large, this factor becomes large positive, this factor becomes large positive, and the product of two large positive numbers is again a large positive, so that limit is infinity. But if we approach negative infinity, let's see what happens there. So we're taking the limit now as x approaches negative infinity of that factored function. And so if I put in a large negative number into this factor, that becomes a negative factor. And if I plug in a large negative factor, a number for x into this factor, we would get a negative number, but then we square it. And the product of a negative, two negatives being squared is a positive factor. And so this whole result comes out to be a positive expression. And so, the product of these two is a negative expression. Negative times a positive is a negative, and so we get negative infinity as we approach, as the domain values go far to the left. So this long-term behavior, and although we didn't have to do it in this problem, this examining the exclusions of the domain when we look for our vertical asymptotes and our holes, well, this procedure requires us to use the limit techniques all the way back in Chapter 2. So if you're rusty on those limit techniques, I highly encourage you to go back and revisit those. Okay, the next thing we want to do is we actually want to put to use all the skills we've been learning in the last 3 or 4 sections of this course. We're going to look where the function's increasing, where it's decreasing, where it's concave up, where it's concave down. We're going to search for the local maxes and mins and the global maxes and mins where applicable, and we're also going to look for the inflection points of this function. So what we should do first is find the critical numbers of both f and f prime. Okay. So let's see what we can do here, folks. So to find the critical numbers of f, we're going to take f's derivative. We get f prime of x would be 3x squared minus 6x minus 9. And let's go ahead and put this into factored form. We can factor out a 3. That leaves us with x squared minus 2x minus 3. And so we can further factor that as 3 times x minus 3 times x plus 1. And so we find that the critical numbers of f, notice that f primes everywhere are defined, so the only place we have critical numbers is where the derivative is 0. And that happens at x equals 3 or x equals negative 1. The next thing we're going to do is we're going to find the critical numbers of f prime. So to do that, to find the critical numbers of f prime, we're going to look at f prime's derivative. So we're going to look at the second derivative of this function. So that happens at 6, or the second derivative is 6x minus 6. And if we set that equal to 0, and factor this, we get 6 times x minus 1. And so we see that x equals 1 is a critical number of f prime. Okay. So at this point we're going to make a chart, and we did this chart once before in this class, but now we're going to actually formalize this procedure. So let's be careful with this. I'm going to make a number line. Then what do I put on the number line? I put any endpoints for this function. I put any exclusions in the domain of this function. I then put any critical numbers of f and any critical numbers of f prime. So I'm going to go ahead and I only have to put 3 values on this particular function. We're going to put in -1, we're going to put in 1, and we're going to put in 3. And let's just note why each one of these is up here. We're going to put in x equals -1 because that's a critical number of f. And similarly, we put in 3 because that was also a critical number of f. And then we put in x equals 1 because that's a critical number of f prime. Then what am I going to do? Well, I'm going to take my test points, or I'm going to select test points, one from each region that I've created. So let's see here, -1/2 and 2 and 4. And then I'm going to plug those test points first into the first derivative and then into the second derivative. Okay. So plugging in -2 into the first derivative, and I'd like to go up here where I've put the first derivative into factored form. If we plug in -2, both these factors are negative. The product of two negative factors is positive, and so we get that the function's increasing on that interval there. If I plug in -1/2, this factor is still negative, but this factor is now positive, and the product of a positive and a negative is a negative factor, and so we're decreasing there. By the way, since this was a critical number of f, notice that we've just shown that x equals -1 is a local maximum. Okay. Then let's see here. We'll plug 2 into the first derivative, and that gives us 3 and -1. And the product of those two is negative, so we are decreasing. And if we plug in 4, notice both these factors are positive, and so we're increasing here. By the way, what have we just shown? We've just shown that x equals 3 is a local max. Okay. So we got all that information. We determined where the function was increasing, decreasing, and by the first derivative test, we determined where we had local maxes and local mins. So the next thing we want to do is we want to plug those test points into the second derivative, and we'll go ahead and do that right here. We'll plug those test points into the second derivative. If I plug in -2, notice that this factor is positive, this factor would then be negative, so we are concave what? If we've got a negative number for the second derivative, that tells us we're concave down. If I plug in -1/2, we're still negative, so we're still concave down. If I plug in 2, that whole expression evaluates to be something positive, so we're concave up, and if we plug in 4, we're also concave up. Okay. So folks, at this point, what else can we identify? Well, at this point we could identify that x equals 1 is an inflection point. Why is that? Because -1 was a critical number of f prime, and it was a place where we changed concavity on this function. That means it must be an inflection point. The concavity changed at a place where this function was defined and continuous, so it must be an inflection point. Okay. So now we're ready to actually sketch this function. Let's go ahead and plug in all of our information. We said the domain's all real numbers, so we don't have to worry about having a starting point to our domain or an ending point. Okay. That was the first statement that we made, that the domain was all real numbers, so there's no starting or ending point. Then we go ahead and we plot our zeros. So we know we've got a 0 at x equals -3, so we've got a 0 right there, and another 0 at x equals 3, and that one had multiplicity 2. We go ahead and plot our, so that was from this information here, we go ahead and plot our y-intercept. Well, we said that when we plug in a 0, it's going to output a 27, so about right there is our y-intercept. Okay. So there's the ordered pair 0, 27 for our y-intercept. And this was -3, 0. I'm just labeling our points. And this was at +3, 0. Okay. Now we're ready to put all of this information together. We know that the long-term behavior, so first of all, we have no vertical asymptotes or holes. We know that the long-term behavior, as we go far to the right, the y values must approach infinity. So as we go far to the right, our y values must end up there. As we go far to the left, our y values must go to -infinity. So that tells us that we're going to enter the graph from down below here. Then the last thing I need to do is label any local maxes and mins that I've got on here. So let's see here. We said x equals -1 is a local max. Okay. So let's go ahead and plug -1 into our original function. So let's see here. What would be f of -1? If I plug -1 into the original function, if we plug -1 into the original function, let's plug it in here where it's in factored form. That would give us -1 minus 3 is -4. Quantity squared is 16, and this would give us a 2. So we get a 32 at -1, and right there we've got our local max at the ordered pair -1, comma 32. Then also we said that x equals 3. Let's see, did we say x equals 3? Yeah, x equals 3 is a local max. Oh, excuse me, we said local max. It should be local min here. I miswrote that. So we said x equals 3 is a local min, and we've already got that location right there, so we know that this is also a local min besides being a 0. And now we're just going to use this chart right here that says we start off increasing in a concave down manner until we get to x equals -1. So I'm going to be increasing in a concave down manner until I get to x equals -1. At x equals -1, I'm going to start decreasing, also in a concave manner, until I get to x equals 1. By the way, if we plug 1 into the original function, what does it spit out? If we plug 1 into the original function, it spits out a 16. So let's see, that will be the place where we have our inflection point. So that's right here. That's the inflection point at the ordered pair 1, comma 16. And the function begins to decrease after we get to -1. So we're going to decrease in a concave down manner. And we're going to continue in a concave down manner until we get to x equals 1. Because at x equals 1, we continue decreasing, but now in a concave up manner, until I get to x equals 3. So I'm going to continue the graph decreasing in a concave up manner until I get to x equals 3. And then at x equals 3, we're going to continue in a concave up manner, but we're going to start increasing. And so our graph would look something like this. And what's pretty amazing about this is we didn't have to do a whole bunch of point plotting, anything like that. We've got all of the interesting locations on this function. We've got the y-intercept, we've got the zeros, we've got the inflection point, we've got the local max, we've got the local min, and the behavior as we join all those points together is accurate for what this graph is doing for this cubic. And so we've graphed this entire function just using our college algebra tools and our tools from calculus. Folks, if you have any questions on this, please let me know.